Hello, everybody. So what we're going to be looking at today is section 4.1, which is functions of several variables. So there are four topics that are in the section, and I've listed them here for you. So first thing we're going to do is we're going to learn how to recognize a function of two variables. Should be easy. You can count to two probably. And we're going to be able to find domain and range of that kind of function. Really, it's going to be domain that you're looking at. The range is often hard to find on these, but at least the domain is relatively simple generally. Um, you'll do that. We're going to be able to make graphs of these kinds of functions, functions of two variables. You've already done that actually. When we did hyperboloids and, hyperboloids of two sheets, of one sheet, hyperbolic paraboloids, that kind of stuff, um, those were functions of two variables. They were x, y, z, but you'll see that it's really the same in this section. So you'll just do what you did in that section. What else are we going to do? We're going to sketch traces or level curves for those functions of two variables. Again, that's something that's related to something we've already done. We will just be doing it again. And finally, we are going to identify the level surfaces of a function of three variables. That's a new thing, but yeah, we'll get to it and we'll see how it goes. It's not so bad. So anyway, that's what we're going to be doing in this section. So let me just kind of also, just before we do this, remind you of what we did last so you can see how this is different. So in the previous chapter, in chapter 3, we looked at vector valued functions. So vector valued functions were like this. Like, this isn't the only way they could be, but this is how we saw it, right? We were looking at things like r of t equals, some function of t. And the point is that your input was one variable, right? Your input was one single variable on these, was a single parameter. And the output of the function was a vector. Okay, that is not what we're looking at here because, well, let's start with this definition of a function of two variables. So our definition, see here, is like this. So z equals f of xy is a function that maps uh, each ordered pair in a subset D of R2 to a unique real number Z. Okay, and then D is called the domain. That should make sense to you because if you look at this, right, you're plugging in the XY and the XY, each ordered pair in a subset D. Well, the ordered pairs are the XYs and they're in the subset D. So things that are in D are going in for XY. And then if that's the input to the function, then that's what a domain is. So yeah, D is called the domain of the function. The range of f is going to be defined as follows. The range of f is the set of all real numbers z um, that have an xy such that z equals f of xy. And all that is saying, and they have a little picture here. I'll draw the picture. So the idea is like this. So you got like this set here is your domain. And so everything in the domain is an x comma y. And then you take that x comma y, you apply the function f, and that takes you to the real line, the number line. And somewhere on here, there's your z. And so this is the range over here. The point is that your inputs are x, y's, and your output is a single variable, as opposed to the previous sections where your input was a single real number and your output was a vector. So it's almost backwards here, right? Compared to what we were looking at in the previous chapter. So this is a new thing for you guys, a little bit. So I just wanted to make it clear that this is different, right? Because we're inputting more than one variable and what comes out is a single variable. And that's not what was happening previously. So there you go. So let's try to just answer a couple questions here about maybe domain and range. So let's say find the domain and range of, let's say A. It's going to be our first function. It's going to be f of xy equals 3x plus 5y plus 2. Okay, and so the domain is where we will start. That's going to end up relatively simple here. And yeah, so let's try to do that. So domain. All right, so just looking at 3x plus 5y plus 2, I see that all x's and y's are, will give you a number here, right? So they're all fine. So looking at this, I see all x, y that exist in R will give you a valid output here. I'll just say are fine to plug into that function. So the domain is actually all of R2, right? R2 means, all x's and y pairs, every x and y. Okay, so that's the domain, everything. And for the range, basically the range is all of the possible outputs, right? So like you have your domain, which for us is all of R2, you apply your function and you get real numbers. Now you don't necessarily get all real numbers. Sometimes you only get some real numbers. So basically what you want to do is look at this function and, figure out like what kind of outputs would this function have. And it doesn't take too much to see that actually all real numbers is going to be the range. And here's one way to show that all real numbers is the range. So, choose any z, right? So choose any z. And then let's look at z equals 3x plus 5y plus 2. Now let's just choose like y equals 0, because why not? Right? So now I have z equals, if y equals 0, just 3x plus 2. Right? Is there a solution to that equation? Right? Can you find an x value to make that true? You can, right? For any possible z, this would have a solution, right? This has a solution, right? How would you know that that's true? Well, if you take that z equals 3x plus 2 and you simply solve it for x, right? Z minus 2 equals 3x. x equals z minus 2 over 3, then no matter what z you pick, this would be the x that makes it possible, right? So for any z value, xy equals, for the x value, you would need z minus 2 over 3. And for the y value, you would need actually just y equals 0, right? Because way up here I said, let's just assume y equals 0 because we didn't need anything complicated there. So for any z value, that right there would produce the z value. Right? And just to double check, right? I mean, this is way more work than you need to do. Like, you should just convince yourself that, like, you can probably just convince yourself that if you look at this function, just like, oh yeah, could you get big negative numbers from this? Sure. Could you get big positive numbers from this? Sure. Is there anything that you can't get from this? No, right? Like, put in big numbers, put in small numbers. You can make big numbers, you can make small numbers, you can make 0, you can make everything. So as soon as you know that, right, you're done. You don't really need to do tons of work like I'm doing here. So just, be advised that I'm doing more than I need to here to try to explain the concepts. So for any z value, that produces z. So just to double check that this is true, right? What is f of, if I put this in for my x and y, right? If I put that in to the function, right? This function here, 3x plus 5y plus 2, you have 3x plus 5y plus 2, right? And if you simply work that out, the 3's cancel, so you just have z minus 2 plus 0 plus 2. And then you just have z because it's z minus 2 plus 2, which is z. So that's proof that you can make that z value from these particular x's and y's. And the point was about z that this was for any possible z value that you would choose. So all possible z's are the range. So our conclusion here is that since all z values can be produced by f, the range is going to be all real numbers. Okay. Again, that was too much there, but we did it. All right. Now let's look at a different one here, where maybe the range is going to be a little bit restricted. So let's look at g of xy equals 9 minus x squared minus y squared. And again, what we're looking for here is domain and range. Right, actually, I think I called that one A, right? So let's just not call this example. Let's call it B. B. Okay, we're looking for the domain and range. So for this one, we know that it's not quite this simple, right? Because when we're looking for the domain, we know that with a square root function, what you plug into a square root can't be negative, right? So because of the square root, we would need 9 minus x squared minus y squared, the thing inside the square root, to be non-negative. So it must be greater than or equal to 0, right? And then once you write that down, you can just rearrange this by putting the x and the y over to the other side, and you would have 9 less than or equal to x squared plus y squared. Or if you don't like writing it that way around, you can go x squared plus y squared less than 9. Okay, now how would you write that? Well, basically what you do is you just write it in what we call set builders notation. So you would say like the domain is the set, right, curly braces for set of all x, y. You could say exists in R2. That's kind of optional. Such that you usually just write a vertical line to indicate such that, and then whatever the restriction is. And so the restriction on the x and the y's is that they satisfy this inequality, right? So you just say that. So all you're really saying is all x, y that satisfies this equation. But this is how you can write it in set builder's notation. Okay. And so what does that actually look like? Well, I mean, you should be able to figure that out, right? Like we're plugging in x, y pairs which exist on the x, y plane, right? And you know that x squared plus y squared equals 9 is a circle, right? So actually, if you make a circle here, then if that circle is radius 3, then your region here for the domain, maybe I'll call it like D. We were supposed to call it D, right? Over there. D equals. Then you've got this circle with radius 3, and the inside of that circle there, actually, I don't want to do that. I can actually shade it. That's the domain. So inside of that circle, that's where x squared plus y squared is less than or equal to 9. Okay, so that's the domain in a picture, and that's the domain written down. Okay, so now what we want to do is we want to look at the range. So just like before, we want to look at our function, which was here. Let's just duplicate it and move it down. So we have this, right? So you have to do a little bit of thinking actually here. So it's a little bit, more complicated than you might think. So if we're looking at this, what I notice is this. So I notice, first of all, that because of the square root, the output of this function has to be greater than or equal. Because of the square root, that the g of xy, of course, I'll just write it, 9 minus x squared minus y squared. That's going to have to be, I wrote greater than or equal to 9. That's wrong. Greater than or equal to 0, right? Just because by definition, the square root function never gives you a negative number. So we can start there. But then you have to actually look a little bit deeper at what's inside the square root, right? I could get a 0 from this, right? For sure, if I put in like certain values for x. I can see, I also see that for some xy, I can get 0, right? Like example, like xy equals like 3, 0, for example, right? F of 3, 0 is going to give you square root 9 minus x squared, which is 3 squared minus 0 squared, and that's 0, right? So I can see that. So that's the smallest value you can get is 0. What's the largest value you can get out of the function g? So the largest value we can get out of this function rewriting again so I can point to it. So how big can you get this function to be? Well, it's 9 minus something positive, right? So the biggest you can actually make the inside here is going to be 9, right? Because it's always 9 minus something, right? This is, let me write it a little nicer here. Like 9 minus, for example, x squared plus y squared, right? So this is square root 9 minus something positive. Nine minus something positive or 0. Right? So you need to be able to look at this and recognize that the biggest you can make this square root is going to be square root 9, right? So the largest you could make it is if you plug in 0, 0, you would have square root 9 minus 0 squared, right? Which would be 3. And kind of combining our information here, right? We know that this is greater than or equal to 0. We know that the biggest it could be is 3. I think it's clear that you could probably make all of the values between 0 and 3 just by picking different x's and y's, right? I don't really want to solve it, but we could do that. Similar to how we did the previous problem. But I'm just going to say, 0 to 3 will work, right? Like I think we can get 0 and 3. So values produced by f are in the range 0 up to 3, right? Just looking at the f and doing a little bit of thinking, that's what we would get. You could also, how we did this up here on this one, where I actually just said like, where did I do it? Just like when like z equals, and I just said, sorry, for any possible z, you can write out like, oh yeah, choose any z, look at this. So you can do the same technique for the problem that we just did, and actually just say like, okay, for any z here, for any z equals this, can you find a solution? Now, of course, the answer is no, but if you do try to solve it, you'll get more information that will helpfully, kind of pin you down on this interval for the range, right? For the biggest and smallest values there. I'm not really going to go into it more than that. That should be fine. Okay. So once you kind of have like basic knowledge of this, you should be able to do other things too. I know that the homework will just make you evaluate functions. Like they'll just give you a function like this. They'll just say like, suppose f of x, y equals, they'll just go like, okay, well, what if we just do, e to the x plus 2xy minus sine y, right? There's a function. And then they'll say evaluate at, xy equals 1 comma pi or something, right? And then they just want to make sure that you're comfortable plugging that into the function. So all you would do there if you have to evaluate this is just say, okay, well, 1 comma pi, just plug in, is all you're doing there. So f of 1 comma pi is just plug in the 1 for x, plug in the pi for y. So you have e to the 1 plus 2 times 1 times pi minus the sine of pi. You work that out on a calculator, on Wolfram Alpha, or by yourself, and we get that e to the 1 is e. 2 times 1 times pi is just 2 pi, and sine pi is actually 0, so there you go. So it's just e plus 2 pi. That's your answer there. So I mean, there are some things like that on the homework, which are nice, right? Nice and easy. So you can do that. You can talk about the domain and range, which we already have, and we should be able to figure out how to graph these kinds of functions. So there's, let's see. The main method to do this is what we call level surfaces. Let me just say we're going to be graphing these functions now. So this is 2 variables in particular. All right. So let's just kind of summarize what we're looking at here. We're looking at z equals fy. So suppose z equals f of xy. Um, the x and the y are what we call the independent variables because they're called independent, right? Because we can let them be anything, potentially. Uh, the z is a dependent variable because in order to know what z is, you have to calculate it from the x and the y, right? So x and y are chosen freely, but the z has to be calculated from the x and the y. So the z is the dependent variable. Okay. Um, so yeah. All right. So in general, um, function is okay, hold on. Okay. So if you take if you take, let's say, z equals f of xy and plot all of the points, the set of points x, y, z, right? Because there is an x, there is a y, and there is a z here. So if we plot the set of points in 3D, what we end up with is a surface. And then this is just a reminder, in the previous chapter, we were looking at vector valued functions, and those were giving us curves generally, right? We spent a lot of time talking about curves, tangent line to curves and things like that. So in 3D, we end up with a surface here. In chapter 3, we were dealing with surfaces. Sorry, no, we were dealing with curves. And I'm just trying to mention this just because the hardest part about this class is keeping everything's like separate in your mind, right? So you don't want to mix up this stuff with the stuff you did for curves, um, so on, right? Like it doesn't make sense to find tangent lines here because we're dealing with surfaces, not lines, curves. All right. So anyway, what are we doing? If you take z equals f of xy, plot the set of points, you end up with a surface, right? Why? Because I said so. We will see that that is the case. All right. So there are different ways to do this. Here's one idea. Yeah. So there are a few ways, uh, a few techniques that will help you do this. Help you plot these surfaces. All right. So let's see here. Do we want to talk about level curves or traces? Let's see what they do. I guess level curves. Yeah. Okay. Level curves. Okay. So again, we're going to assume that we're looking function of, z equals f of xy. So consider f z equals f of xy, right? If you set z to a particular value, like for example, z equals 1, um, then you will get the equation of you'll get an equation in xy, right? So if you set z to a particular value like z equals 1, you get 1 equals f of xy, right? Now that's a function of two variables. That means you can plot it on a 2D plot. You can plot this curve on a 2D, XY plot, right? Now, if you do that for several different z values, so if you do that for several different z values, you get several curves to plot. You get what we call level curves of, I'll say, like equal elevation, that we call level curve. So for example, like suppose I was not going to do this yet, but I guess I am now. So like suppose we have a function like this. So let's say consider f of xy equals, let's just go like 16 minus x squared minus y squared. Okay, so there's a function. All right, now, and you could say like z equals f of xy equals 16 minus x squared minus y squared. So here's the idea that we're doing. If you take several different z values, right? So take a few. Usually you do like 3 or 4 if you're doing them by hand, and see what we get. So if I take z equals 0, right, and I'm setting z equals 0 here and then keeping the rest of the equation. So it's like z equals 0 says 0 equals 16 minus x squared minus y squared. Move the x squared plus y squared over to the left, right? And what we'll get is x squared plus y squared equals 16. All right, let's pick a different z value. Let's say like, let's go z equals 1, for example. Then we get 1 equals 16 minus x squared minus y squared, right? Which, if you move the x squared plus y squared, if you move this part over to the left and you move and you move the 1 over to the right, this would be x squared plus y squared equals 15. Okay, now if you do like z equals 2, you get 2 equals 16 minus x squared minus y squared, which is, x squared plus y squared equals 14 eventually. I realized I was thinking that I should have, I was thinking that the square root of 16 was going to be important when I wrote that number down, and it's not. I really should have used a small number here. So I'm actually going to skip these, I'm going to skip some z values here, right? Because this is going very slowly, right? 16, 15, 14. Let's put like bigger numbers here. So like, let's say like z equals 10, right? So you got like 10 equals 16 minus x squared minus y squared. Rearrange that, it'd be like x squared plus y squared equals 6. For example, z equals 12 would be 12 equals 16 minus x squared minus y squared, which would give you, after we rearrange it, x squared plus y squared equals 4. Okay, that's one more. 2 more. I said do 3 or 4, and we're doing like a whole bunch. And we're doing a bunch because, like I said, I picked the numbers badly. So like, let's do 15. you have 15 equals 16 minus x squared minus y squared. Rearrange it, it would be x squared plus y squared equals 1. And if I do z equals 16, I have 16 equals 16 minus x squared minus y squared, which is x squared plus y squared equals 0. And if you even go one higher, like 17, you have 17 equals 16 minus x squared minus y squared, which is, if you rearrange it, x squared plus y squared equals -1. Okay, we did way too much there. This was way more than I needed to do, but I did it for a reason here. Again, the reason is that I'm done. All right, let's go to this plot. So we're looking at a 2D plot of these. So we're not going to plot all of these. Let's plot some of these. So if you plot this one, right? The equation that we came up with is x squared plus y squared equals 16. You should recognize this as a circle with radius 4. So this is a circle with radius 4. So you plot this function here, x squared plus y squared equals 16, on this graph, which let me just actually make it line up with the graph. Okay, so you plot that. So we go circle. We want this to be 4. Did I get 4? No, I got 5. Okay, 4. All right, now that's a circle. And this in particular was the z equals 0 circle. Okay, now let's plot another one of these. I only want to plot the ones that are even. So like we did 16. Let's just do this one. The curve here is x squared plus y squared equals 4. That's a circle with radius 2. So let's plot this. Circle with radius 2, we know it is. That was terrible. Okay. So this was actually z equals 12. We also have like z equals 0 here. This one. X squared plus y squared equals 0 is actually just a single point, 0, 0. So right here in the middle, that's z equals 16. Okay, and so what that's telling you here, so these are your level curves. I mean, only a few, right? We literally could have plotted all of these. It's just that, like, you know, radius square root 15, radius square root 14. I didn't want those. Now I could have put like the one that was radius 9 in, but I didn't. It would have been, you know, in between here. I just didn't pick the right values. So let's just look at this. These are the level curves. Now, how does that tell you anything about the 3D plot? Well, it tells you a lot about the 3D plot, right? Because what it's telling you that why did I put y there? You have your x, you have your y, you have your z, and it's telling you what's going on. This curve here is saying that at z equals 0, right, which is the ground floor here, we should have a circle with radius 4. So you draw your circle with radius 4, you know, down here, which something like that would be what you got. So this is your like z equals 0 level curve. Okay, but then you've got your z equals 12 level curve. Well, where do you draw that? You draw it way up at z equals 12, right? So like way up here somewhere you have z equals 12, and you got this circle with radius 2, so half the radius. So you got one of these guys up here. That's a little bit crooked. I don't know what got changed. I'm gonna plot one of these to look decent. Okay, that's good. Okay. So that's what you have up at z equals 12, something like that. And then you have at z equals 16, just a single dot. So you go up a little bit higher, z equals 16, and then right at 0, 0. And, we could have plot these, a lot more level curves. The more level curves you have, the more helpful it is. But, we're going to connect these points here. Hey, come on. Okay, whatever, good enough. So you get this kind of shape here, which we didn't really plot a lot up at the top, but there we go. So if you had plot more level curves, right? Like if you had plot one in here, right? Like that'd be like the z equals, like let's say that's the radius 3, 1, which in order to get 3, you would have to have 9, which is 16 minus 7. So this would be like the z equals 7 level curve. So, you know, in here somewhere was z equals 9, for example, level curve. And you can plot as many of them as you need in order to understand the shape of the surface. So the surface is actually the outside of this shape, right? So the whole, like the actual surface of this 3D object is the thing we're plotting. These little ellipses here, or circles actually, that we're plotting are just traces. Okay, so this is your 3D surface that we get. And hopefully this did look familiar, because we did a little bit of this in the section where we talked about elliptic paraboloids and hyperboloids and all of those, cones and so on. So yeah, so these are called level curves, and these are 3D surfaces. And what you want to get used to doing is this idea that you can take like z equals something, just simply write your function equals that z value, and that gives you a 2D plot. Okay? And then you can make 2D plots out of these. So this is your, you plug in your z. And for these, this is, the resulting equation of the level curve or trace. Okay. So then we plot our level curves. So those are level curves, and they help you plot things, just like you saw us plot this elliptic paraboloid here. Okay. That's not the only thing you can do, but it's one of the things you can do. They do have a definition of this, so I will just write out their definition as well. So given a function, z equals, actually they don't even use z there. They just say given a function f of x, y, a level curve of f, for the value c, is the equation f of x, y equals c. Right? That's what we were doing here, right? It was z was what we had on the other side of the equation, but this was f of x, y, and this is the c. F of x, y, c. F of x, y, c. So this is just what we just did, but they have the definition afterwards. Okay, so that's those are level curves. Now, another definition is if you plot several level curves on a 2D plot, a plot of several level curves on a 2D plot is called a contour map. Okay, and a contour map is basically just like, like a topographical map, like for like mountains or something, right? So like, if you had like some kind of level curves, right? Like if you had like a dot here, if you had a dot here, and you had like one of these, this, and maybe like this, and then maybe like this, right? You have something like this, where like maybe this is like z equals 0, z equals 1, z equals 1, z equals 2, z equals, let's say 4 actually, and let's go like z equals 6, and then this was like z equals 3 in there. Okay, like if you have some map like that, then again you would be able to like make a 2D plot here just by the map in 3D space. You say like where's the highest point? Well, like maybe that this is z. If this is z equals 6, that looks like the highest point. The way it's drawn, it's like it's over here, maybe at 6, and then below that as z equals 4, you got kind of just the shape here at like 4, and then as z equals 3, you got this peak, which is on the other side. So like maybe at 3, you got like peak over here. Um, and then at z equals 2, you got one of these. And then at z equals 1, you got this one, which is down here. And then at z equals 0, you've got kind of just this thing. So it's all just kind of in the XY plane. And so what you're seeing there is that there's actually some kind of peak there and peak over here that that you're getting. So there's like this is what a mountain looks like. You have a little mountain there, and then over here you have another little mountain. That one's smaller because this is like z equals 2, z equals 3, whereas this is z equals 4, z equals 6, twice as tall. But yeah, so you can tell what's going on, right? Like it's just like a map of elevation is what you're doing when you're making these contour maps. Okay. All right. So let's see here. So something they ask super often in the homework is just a question like this. They just say, example, find the equation of the level curve um, for, let's just say like z or c, depending on how they feel like saying it. I'll just say z, like z equals 7 for f of x, y equal, and it's just whatever it is, right? So it's just whatever equation they give you. So like square root, 100 minus xy, right? And there's really nothing to this, right? You simply just say like, okay, so z equals 100 minus xy, and z equals 7, so 7 equals square root 100 minus xy, right? Um, so there's really nothing to do there for finding the equations of the level curves. It's super simple. They just want to make sure you understand the concept. Okay. Now, another thing you can do other than just level curves is something closely related called vertical traces, which usually I won't do at all, but because usually level curves are easier for me, but you can do vertical traces. And so here's the definition. They say consider again z equals f of x, y, function of two variables with domain d, some subset of R2. So that's just, a function. they're not saying anything there. So a vertical trace um, can be either um, the set of points that solves um, f of like ay equals a constant for like ay equals z for a constant a, or yeah, constant x equals a is how they say it, or the set of points that solves, let's say, f of x comma b equals z for a constant y equals b. Okay, so it's really the same kind of idea as for a level curve, except that this time is the x or y is the constant. Okay, so it's like level curves, except equals x or y equals a constant. Okay, so why would you want to do that? I don't know. Maybe you think it's going to help you make a plot. So let's see here. Can I even find a worthwhile one? I think so. So let's see here. Um, let's see. For f of xy equals sine x cosine y, find vertical traces. I'm going to say for x equals 0 and x equals, let's say, power 2 and x equals. Now, we could have done those for y, or some of them y, some of them x, right? We're just making traces. So, um, there was no restrictions on what we're doing, except that couldn't be z because z is a level curve, not a vertical trace. All right, so what do you do? Same process, right? So for x equals 0, you would plug that into your function. So f of xy, actually f of 0y, right, is going to be sine 0 cosine y, which is actually just 0. Okay. And then your x equals pi over 2, should have done y, but for x equals pi over 2, um, we have f of pi over 2 comma y equals sine pi over 2 cosine y. Sine pi over 2 is 1, so we just have simply cosine y. And then x equals, wait, what I do? Yeah, pi. Pi, f of pi y is going to be sine pi cosine y. Sine pi is also 0 again. So these aren't the most interesting traces in the world, but what they could help you do is make a plot. I'm going to have to, let's say, put, this will be a little bit tricky. Put x there, put y there, put z there. Okay. So the idea is, so like x equals 0, x equals 0 is the YZ plane. So like, right, like the back wall. Actually, I don't want to even write it like that. Like let's just go from the ground up, right? Like this is x equals 0. And what about x equals pi over 2, right? That's further in the positive x direction. So like, let me pick a different color. So like if you come out here to pi over 2, then you draw another one of those. Actually, again, I screwed up the drawing. Right, like this is x equals 2. Why I wrote that so small and hard to read. All right, because this is pi over 2 here. And then if you came out even further, you'd have like x equals pi, and that would be even further forward, right? And so these traces that we were doing are vertical traces. So like the first one here, which is just um, 0, so f of xy, which is the z value equals 0, right? You apply z equals 0 in the xy, or in that x equals 0 plane, which is right here. So like z equals 0 is just completely flat. So like there. Okay. And then the x equal pi over 2 plane, that's the green one. The equation is cosine y, which again, it's like z equals cosine y. Uh, so you're plotting it in the yz plane. So in the green box, you'd be plotting cosine curve. So like cosine curve is up at 1 and then goes down and then back up and down. And that would be in the green plane, which I didn't draw a green. Maybe I should draw a green. Okay, so like, I'm to plot a cosine here. Okay. And then if you go out to the pink curve again, then the function is flat because this is like z equals 0 again. So that's actually like a weird plot. Let me see if I can plot this in GeoGebra. We may fail, but we'll try it. GeoGebra. And hopefully we'll be able to see what we just came up with. Because what I just plotted is just almost impossible to see anything. Let's switch to the 3D plot somehow. Nope. 3D calculator. Here we are trying to plot the original function, which is f of xy equals sine x cosine y. Okay, so that's, z equals. So let's see if we can, first of all, figure out how to scroll here. That's completely useless. Why? Delete tools. Calculator. I need the calculator to scroll. Okay. So like if I go z equals functions, come on, sine x times cosine y. Okay, so we're looking down on it. All right, cool. So here's what you want to see though. Man, I can't really point to it. I'm gonna take a plot of this. Hold on. I don't know which one's X and which one's Y, which one's Z here, but this one will work. I'll assume this is oriented the way we wanted it. Let's screenshot this. So let's just still this so I can draw on it. Done. Save to photos. Okay, boom. There it is. A lot of work to go through, but this way we can draw on it. So what I wanted to do on this was just show you where these things are. So like the this one right here, z equals 0, is at x equals 0. So let's just say that I don't know if green or red was. No, I do know. The green's got to be the y-axis. So basically, this right here is just flat at 0 um, when x equals 0. On the graph, that's right here, right? You see that the surface is actually just completely horizontal right there. Then you've got this at x equals pi over 2, you've got a cosine wave. And so where is that on the graph? Well, if you come further this way, right, then right here on the top of this graph here, you've got a cosine wave. Right, so that's this green cosine wave. And if you go out further in this direction, then you get this pink curve, which is again just flat like it originally was. And that is hard to see, but it's going to be right here. So it's flat at 0, and then in the middle it's wavy, and then it becomes flat, and then it becomes wavy again. And same thing going backwards, but we didn't do those vertical traces. Flat, cosine, right here it's perfectly flat, and another cosine type wave. And there you go. So hopefully the pink flat, orange flat, green wave, you can see here. Orange flat, pink flat, green wave. Okay, and those are vertical traces. And they're called vertical traces because these curves that we're doing live in these vertically oriented planes, as opposed to the level curves on the contour map, which these curves were in vertical planes. So they were horizontal curves in vertical slices. In horizontal slices. This was in a horizontal slice, horizontal slice, horizontal slice. Whereas the vertical traces are all in, vertical planes. Okay, so that's why they're called vertical traces, and that's how you do them. Okay, so those are vertical traces, and I think what haven't we done? I think the only thing we haven't done now is um, identify the level surfaces of a function of 3 variables. So everything we've done up till now was 2 variables, right? So when you've got 3 variables, it is different. So let me talk about it. Functions of 3 variables. Okay, so we just saw this. We just saw that z equals f of x, y gives you a surface in 3D. Right? We saw that. The other thing we saw was that if you fix z to be a constant, if you set z equals constant, you get what we call a level curve. Okay, so the original thing is a surface, and if you set z equals a constant, you get a level curve. Okay, now if you've got a function of 3 variables, then that's not going to be the case. So let's consider a function of 3 variables. what's a function of three variables like z? No, not z. Wouldn't want z. We would just call it f of x, y, z. And if you wanted to equal something, it would have to be something other than z. Right? So there's a function of three variables. Now, what could it represent? So these functions can represent various things. For example, you might use such functions to represent a quantity that varies over space. Like, for example, like maybe, like d equals, and this is completely made up, but like maybe you have something like this, like 5,000 minus x squared minus y squared minus z squared represents the density of an object um, at each point in 3D space. Right? So, like something like that is pretty different than what we had for XYZ, where our main interpretation was that if you have f of xy here, that x and y were spatial variables, and also whatever this was equal to was a z value, which is also like a place in space, right? Whereas this is not. The x, y, z are all things in space. They're all things in space, and the actual number here is calculating something else, like a density or something in space, or like magnetic flux, not magnetic flux, but like charge density in space or something like that. Okay, so they kind of are used for different things, but that's a function of three variables as an example. Okay, now the thing about this though is that if you fix x, y, or z to be equal, or sorry, if you set the function to be equal a constant, you don't get a curve anymore. So that's the main thing that you want to know here, because you're going to have to do it on the homework. So level surfaces. Here's the punchline here. So what we set up here is so for functions of two variables. Sorry, I have to rewrite this. So for f of x, y, we learned f equals constant resulted in a level curve. A level curve you can plot in 2D in the 2D XY plane. But for a function of three variables, for f of x, y, z, when you set f equals a constant, you actually get a function of all three variables. An equation with all three variables generally. And if you get an equation with three variables, that defines its surface. Not a curve. Okay, so we call these level surfaces. So if we go back up to our definition of level curve, which is somewhere, here it is. Oh no, that's not what it was up here. Here it is. duplicate, come down here, and we'll put it down. So here is our function of a level curve, right? If you simply erase the f of the xy and we say f of x, y, z, and then we erase the word curve and write surface, and the same thing here. And so all that's going on here is that when you add this third variable here, then f of x, y, z isn't a curve, it's the surface. So yeah, so that's how you define a level surface. So you do it in the exact same way. So there's nothing really to it. Example, let's say find, let's say 3 level surfaces to, let's say, d of x, y, z. Actually, yeah, let's do that. D of x, y, z equals, let's say, square root. Do I need square root? Yeah, I mean, I guess so. Let's do numbers that make sense. So let's do 100 minus x squared minus y squared minus z squared. Okay. I'll say, and let's specifically say for, let's do d equals 0 and trying to think here. D equals 19. No, that won't work. Oh man. It's so hard to make the numbers work here. Changing that. $36. Okay. Let's put a 3 there. These numbers still aren't going to work out. I mean, I don't know what I'm doing. Let's do that, and then let's do, we did 3, and then let's do 6. Yeah, okay, let's just do it. D equals 0, D equals 3, D equals 6. Fine. So let's do it. So you do it in the same way that we did the level curves. It's just that the equation won't be a curve. So for D equals 0, then your equation is 0 equals square root 36 minus x squared minus y squared minus z squared. Okay, which you can just square both sides and get 0 equals 36 minus x squared minus y squared minus z squared. Move the x squared, y squared, z squared to one side, and you have this, okay? Now do the same for d equals 3. We'll see what the equations are in a second. So don't, like, I'm not just saying that, but I just want to move on. So if I have 3 equals square root 36 minus x squared minus y squared minus z squared, square both sides again. Again, 9 equals 36 minus x squared minus y squared minus z squared. Rearrange, you're going to get 27 equals x squared plus y squared plus z squared. Let's do d equals 3, or d equals 6, I guess. 6 equals square root 36 minus x squared minus y squared minus z squared. Square both sides. 36 equals 36 minus x squared minus y squared minus z squared. Rearrange, you get x squared plus y squared plus z squared equals 0. Okay, so these are the actual answers to what I said. I said find 3 level surfaces. Here they are. Those are the 3 level surfaces. Now, if you wanted to graph them, what would you be graphing? Well, what you would be graphing are spheres, right? Like you can notice that these are all the equations of spheres, right? Oops. Here, here, right? Not curves, right? They're not curves. Spheres are in space. They're surfaces. Now, if you wanted to plot them, you actually could, but you can't plot them on a contour plot or anything like that. That doesn't make sense because those are for 2D plots for plotting curves and stuff. So what we have is actually like this is a sphere with a radius 6. So if you go to plot that, you get a 3D plot and 1, 2, 3, 4, 6, 6. Right. So that's the circle with radius 6, which came from, that was where d equals 0. So this is like the d equals 0 sphere. And it is a sphere. So like this isn't like, right? So like this is actually a 3D, like a 3D shape here, like a 2D circle that we're looking at. So it's like an entire ball. Now, if you go inside, not inside, if you do the next one, x squared plus y squared plus z squared equals 27, that's also a sphere, but the radius is square root 27. So you'd have to use a calculator to get that radius. So that would be radius of around 5. So this is like 5.2, something like that. So if you were going to plot that one, then you've got a sphere inside the sphere, radius like 5 point something. So like here, do like an egg. So you get that. And that is the A. That is the D equals 3 surface. Now, I don't really think you have to do too much plotting of these, but you know, you got this sphere inside the other sphere. And then finally, you've got this one, the d equals 6 sphere, which is x squared plus y squared plus z squared equals 0, which is just a single point at 0, 0, 0. So if you plot that one, you have just this, and that's the d equals 0. Oh, no, d equals 6 surface. So the point is that this graph of level surfaces is equivalent to the graph of level curves that we did here, right? We got this graph from these kinds of calculations, and it was, you know, a 2D plot of curves for level curves, and for level surfaces, you end up with a 3D plot of level surfaces. Okay, so that is what level surfaces are. You calculate them the same way, right? Like you just set the function equal to a constant, so it's the exact same definition as level curves, except that you're dealing with a function of 3 variables instead of a function with 2 variables. Okay, so I think that's everything you need to know. And so we will stop this lecture here.